So this is extremely open science, and we are streaming right now. See, everything works. Everything works. So we are going to pick up where we left off. Oh, sorry, I am playing it myself.
We are streaming right now.
How do I stop? Okay.
Works. So.
Let me mute it. Okay. All right. So this is where we were last time. So sort of a recap. So last time we had started working on using Progenomes 3 as a data source to get the genomes and annotate them. And so, yes. And so I was going to download Progenomes 3, and I said I was going to. We had created this script to download Progenomes. Where is this? Oh, there it is. There it is. So we had downloaded these. We had downloaded these tables. So actually, we created a script that downloads the table from Progenomes 3, and then the goal was going to be to leave the download script running, potentially over a couple of days, to get the genomes. Now I don't know if anyone tried that, but I tried it. I left it running, and I left it running the whole day. I went into the office, now I'm actually streaming from home, and this is also a special week because it's a holiday, it's the Easter holiday, so it's also a pretty different morning, because my daughters don't go to school as usual, so it's a little bit different so this is also partly why we were late in the morning. But anyway, so I left this running, and I came back several hours later, so at the end of the day, and unfortunately it had gotten stuck. So this code that downloads the genomes had actually not downloaded the genomes, had gotten stuck. And so I did what you do in this situation, which is kill it and run it again. And I tried it, and the same thing happened. So after a while it gets stuck. I mean, between my computer going into sleep mode or some network failure, I don't know exactly what happened. I could have spent a bit of time debugging this. I didn't. I actually tried to stop myself from working on this whilst I'm not streaming. But there's something quick that I think we can do right now to really improve things, which is to make things faster. So here already, actually, I see that all right. So this is good. So it does not download things a second time. I'm not sure, which means that if I run it 2 times, it will keep going. It will not download the same things over and over again. But maybe a little bit more important. So I think for now we can make a lot of progress without having to download all the genomes. We can probably just download some genomes and not all of them. And so, because a lot of this, what we're trying to do is sort of statistical, and so if some of these species or species are very large, thousands of genomes, but in practice, if we have a couple hundred, even 100, that's already more than enough to get the patterns. And so let's have something that selects genome. So the goal here is going to be select or sample I'm not gonna. Okay. Okay, and okay, this could work actually. I don't particularly like it. And I'm going to tell you why I don't particularly like it. I don't particularly like it because it's not deterministic, right? So, I mean, I'm actually just clusters. Okay, so for example, okay, this one. All right, so this one, for example, number 9 has almost 10,000 genomes. This is too much. So how do we sample? So I want to sample this down to a much more meaningful number. So how can I do this? So this works. Problem is, every time I run it, it's going to return the same result, which is obviously not what I want. I mean, or it could be what I want, but it's not the best. So, okay, so we can set the seed. So most people know this, but I'll just so if you set the seed, and you can set the seed to something 1, 2, 3, 4, 5, and then if you do some random operation, it's going to look random. But if you set the same seed twice, then it's going to look less random, or it's going to be it's not random at all actually. So what and then I was just double checking that you can actually set the seed with a string. So I'm gonna set the seed with like this. So this is still not absolutely perfect, because if I run it on my computer and you run it on yours, just because of the way that things are implemented in NumPy, you can get slightly different results if you have a slightly different version of NumPy, or actually completely different results. But at least on my computer, if I run it 2 times, then it will be the same. And just generally speaking, it's nice to have the same results. And actually, let me check something else, which I'm not sure to be. Yeah, so I was just checking this. So I wanted to be sure that this is the behavior. Again, we're a little bit relying on behavior that's probably not going to be always the case, but at least for here, it seems that if I first ask for 4 and then later ask for 4 more, I get these genomes, and if I ask for 8 at once, I get the same. And so you might be asking, so okay, what does that help? That means that later we can increase this number without having to do a lot more. So let's now, for example, now let's just do 10, which is a very ridiculously small number, but it's gonna just be a proof of concept. And then if we increase it to 100, which is now a more reasonable number, then it's going to at the very least reuse some of the downloads, or reuse the downloads from the 10 and only download 90 more, which maybe it doesn't seem that much, but let me just to be sure that something's happening. Okay. Okay, so now this is actually downloading something. Right, so this is much better than this is much better than we had last week. At least in the sense that it's going to actually finish, and it's slightly more robust, or not more robust, but at least, let me see, I'm going to just kill it. Okay. Probably should not have done that. Probably should not have done that because yeah, okay, yeah, so some files get corrupted. Actually, quite a lot. So this is a very, very common thing, and the problem is here, or it's the same here, right? We open the output file and then we write to it, and since this writing takes a while, because this is basically as the file is downloading, if I interrupt the process right here, as if I just press Control-C at a random moment, we probably will interrupt it here because this code is very fast. So establishing the connection maybe takes half a second, and then downloading it takes several seconds. And so if I just randomly pick a time, I'm much more likely to be here exactly halfway through or partially through downloading the file, and not in the and so this will create a partial file. The issue with the partial file is that then it gets created, then later here it gets tested that it exists, and the process continues, assuming that the file is correct, which is wrong. So there's two ways around this. So one way would be to try to be smart and catch the error and not. That would be one way. But the other one is to use, which is what I'm doing here, is to just use atomic writes. But for that, I do need to install. So the standard way of dealing with this problem is to do do a three-step process. So instead of opening the file, writing to the file, closing the file, so that's the standard process. So what we do is we open a temporary file. So that's step one. Write to the temporary file and close it. So that's step two. And then move the temporary file to the final file. And on Unix, and I think this is a bit different on Windows, but on Unix, this move is guaranteed to be atomic, right? In the sense that either the file moves or it doesn't, but you don't get a partial move. And so this means that even if you somehow interrupt, or even if you pull the plug, or we run out of battery to be, at halfway through the process will always be either you have not yet moved the file, in which case there's no problem, you just interrupted before the move, or you have completed the move. But you'll never get what we were getting, which is some sort of partial file. And we can see this happening, so let me execute this again. It's going to take a couple, oops. Okay, and yes, it's atomic, right? Yes. Sorry. Let me just see how does this work. This. How do you write a binary one? I find it actually quite almost a big failure of the language that this is not built into the language. This really should be something that's built into the language, or at least part of the standard library, rather than something that we have to rely on. We have to rely on these packages by third parties. But I think being able to write a file atomically, so that either the file exists or it doesn't. Atomic writer. Mode equals W. Okay, this is what I want. Okay, let's see, finally, all right. So you can see here, for example, there was this temporary file, and actually, see, it doesn't exist anymore. So this is all being done by the atomic write. So it creates these temporary files, and then it will download the data to that. So we write to that, and then once that's done, it will smartly rename it, move it to the final name. So later these names actually exist. And now, if I interrupt it, see, it was interrupted somewhere. Oh, it was interrupted while calling RGI, actually not. It's okay. I'm gonna just force this a little bit. So if I just run a process, so all this does is that runs the download script. So here I'm gonna interrupt it. See, it's being interrupted somewhere while it's downloading something. And now if I go, so I only have one file and it exists, and it doesn't give me an error in the file. Okay, all right. So this was just to demonstrate that these things exist and can work well. Let me just see if there's any other files here that are partial. By the way, and this is, so you can see, by the way, and this is something that's, so this is a JZip file, and so JZip will complain that we have an unexpected end of file. So JZip is complaining that the file is incomplete. If we had been downloading directly FASTA files, we would actually not get this error. So for example, and I can just demonstrate this really quick. So, all right. So you can see that so if all we had was this, how would we know that this is not the partial file? This is a perfectly valid FASTA file, perfectly valid. It has has 11 contigs. Sorry, it's -c. It's a bit, maybe we could see, okay, this is a bit small for a bacterial genome, so maybe we could pick it up from there. But tools like RGI would simply process it, maybe find nothing, or maybe maybe we find something because it's still a fraction of the genome. But it could be quite easy for us to make the mistake of simply, processing this as a full genome without even realizing that we actually have a partial genome. So this is one of the reasons why I'm in favor of always compressing, because compression, first of all, saves disk space. That's pretty obvious, I think, for everybody. But then perhaps less obvious is that it gives you this checksumming for free. So you can do checksums. So if files are corrupt. And most corruption, I think, is of this form where you have a partial file. So there's many ways in which you can get the partial file. So this is one of them is you run you run some process, somehow it gets interrupted, you kill it, or you run out of power, or an asteroid hits your computer at exactly that moment, and then you have some issue there, and if you have a checksum, then that gets picked up quite easily, and and so this is why one of the reasons why I think you should always compress. Okay, so let's just test what's happening. Okay, so RGI is running something. Oh yeah, it's running Prodigal. There it is. Yeah, so this OBS is me streaming, and one of the issues with the streams that I've realized is because I am streaming, so you can see it's using a lot of CPU, so everything else feels very sluggish. I think it's trying to use as many CPUs as it can to encode the video for your listening pleasure or your viewing pleasure, but then that means that everything else gets pretty slow. I guess if we were professional enough, we would have a lot more. We'd have different equipment for the computer, the compute, and the actual streaming. Okay. Okay, oh yeah, we do have. Okay, we have stuff going on. Okay, all right, let's add this to the. Okay, and so remember I said we had this, we were doing this smart thing where we would only download if it hadn't been downloaded before. But then with the way we structure things, RGI would always run, which, okay, maybe that's fine for now, but since we're waiting for it to run anyway, let's actually improve that quickly. So we could do this in many ways. One easy way so we could use Jug itself to do it. Because Jug is actually, this is pretty much what Jug does. So what we do here is yeah, that's pretty much it. Oh, I see. Oh, I see. We need to. I'm gonna actually interrupt all of this. Right. So I realized that. So before we were structured, this was structured such that download genomes returns a directory, and then run RGI runs glob on that directory, which would work, except that now if some directories we've already downloaded more files than we should, so instead I'm so instead the download genome should return all the paths, and then here okay, and does this work? I confess I have not used this compound task generator for years, I think. Years. Yeah, this is not, yeah, okay, this is not what it does. Can I do this? No, it can't. Okay, this. Okay, this works. Right. So what here the transformation is. Okay, so let's do. Okay, there were two transformations. So the first one is that download genomes should return the list of downloaded genomes and not just the directory. The second one is that run RGI for all genomes should check, if the RGI out file exists, then it should immediately just return it. If it shouldn't run RGI again. And then that means too that, we should watch out for what happens if we interrupt RGI. Then here we have to do this two-step of write to a temporary file, move the temporary file. We have to implement it by hand, in the sense that so we have to write this code that does temp and then moves to the temp. This is because RGI itself is not writing atomically. So RGI will write these partial files for us if we let it. Okay, and I think this works. So now, because we have changed the code for download genomes, we actually need to invalidate it, saying, basically we need to tell Jug that, what we ran before shouldn't run it again. But now here, Okay. No, actually, I think. Because I'm gonna do the invalidation again for this, and I am going to oh, okay. Okay, it's running RGI for something. Okay. So RGI is running. Prodigal is running. Okay, so that's something is happening. Diamond is running. RGI is running. Okay, there it is. Okay. Okay, I'm gonna interrupt this. Let's just see if... Okay, and all right, so it did something, it skipped something. All right, I think this is good. I think... Okay, let me check. Yeah, we're sort of towards the end of the session, so I think this is good. So here I got this wrong about how the paths work. So you give it RGI out, and then there's a .txt and a .json. So I write out to a temp, then move the txt and the JSON. And then at the top, I check for the JSON. So even in the very, very rare case where process interrupted between moving the txt and the JSON is the last one to be moved. So if the JSON exists with the right name, then that means that RGI ran to completion without any problems. So it's safe to test on that. Okay, so yeah, this compound thing, we don't need it. Yep. Okay, so it's going. All right, so download genomes returns a list of paths. This is actually better, just generally speaking. It's much more robust. RGI being atomic, this is also much more robust. I mean, things should just be atomic. I mean, actually, our tools generally do a good job with this. So, for example, if you're running semi-bin or anything like that, if you have any output files, those will be complete files. So we tend to avoid these issues, but we are not. This is not the norm, unfortunately. Okay, and now, yeah. So now this is going to be running. I'm going to try this thing again today of just leaving it running, going into work. I think what is nicer about this version of the code is that it's clearly making a lot more progress faster. So probably at some point, we will have to rerun it. Right now it's getting 10 genomes per spec-i, which is obviously way too little, but at some point we will just adapt this to run a lot more. But with that, unless anyone has any other questions, well, the chat was very quiet this week. Right, I will see you all next week.